27 identical charge drops combine to form a big drop. Find the ratio between the potential of a big drop to one small drop. So here charge drops are combining to form the big drop. So what is the ratio of the potentials on the big drop to that of the small drop? So we know that potential on any drop V is equal to 1 by 4 pi epsilon naught into Q by R. Now if I take the ratio between potential on big drop by potential on small drop, it is charge on big drop by charge on small drop into radius of the small drop by radius of the big drop. We already know whenever drops combine, charge on the big drop is n times the charge on the small drop. If n drops combine, n identical charge drops combine, then I can say Q on the big drop is n times Q on the small drop. Similarly, since volume remains constant, from that we can prove radius of the big drop is n to the power of 1/3 into radius of the small drop. So if I substitute these relations into the above equation, VB by Vs is equal to, we have QB by Qs. So charge on the big drop by charge on the small drop, which is nothing but n, into radius of the small drop by radius of the big drop. This is 1 by n to the power of 1/3. So if I simplify it, n to the power of 2/3. Now, so whenever drops combine, ratio of the potential on the big drop to potential on the small drop, n to the power of 2/3. Now let us take n is given as 27 identical drops. So put n is equal to 27 or 3 cube. So potential on the big drop by potential of the small drop is 3 cube whole to the power of 2 by 3. So this 3 and this power 3 gets cancelled. Remaining is 3 square. The value of 3 square is nothing but 9. Therefore answer is 9 is to 1. The potential on the big drop to potential on one small drop is equal to 9 is to 1. Consider another example. Two point charges 16 microcoulomb and 4 microcoulomb are 15 cm apart. Find the potential at the point where the intensity of electric field is 0 on the line joining them. So here two charges are taken, 16 micro and 4 micro. The distance of separation is 15 cm. We are to calculate the potential at the point where the intensity of electric field is 0. So at the points where the intensity becomes 0, we are interested to calculate the potential. So let us consider given charges Q1, Q2. So let us take Q1 as 4 and Q2 as 16, and the distance of separation between them 15 centimeter. What is the distance of the point at which potential intensity of electric field becomes 0? Suppose if I take x is the distance where the intensity of electric field becomes 0. We know that for like charges always 0 intensity electric field point, or it is also called as null point, lies in between. The equation for null point distance, x is equal to d by root over q2 by q1 plus 1. Plus or minus you have to take minus sign for unlike charges and point lies outside, plus sign for like charges and point lies in between. Always Q1 is a smaller charge and Q2 is bigger charge. So substitution gives 15 divided by root over 16 by 4 plus 1. So this is 15 by 4 under root is 2, 2 plus 1, it is 3. Therefore 5 centimeter. So x is equal to 5 centimeter. From the smaller charge, null point exists at 5. Therefore from 16 it is 10 centimeter. Now at this point our interest is to calculate what is the potential. So potential at this point, let us say due to Q1 it is V1. So V1 is equal to 1 by 4 pi epsilon naught times Q1 by x. So this value 9 into 10 to the power of 9 4 into 10 to the power of minus 6 by 5 centimeter, 5 by 100. So if I simplify this one, 9 into 4, 36 by 5 into, take this 100 to the numerator, 10 power 9 plus 2, 10 power 11, so remaining 10 to the power of 5 volts. Now calculate potential due to second charge V2 and its distance is 10. So V2 is equal to again 1 by 4 pi epsilon naught times Q2 by d minus x. Of course d minus x value is 10 and the charge here is 16 micro. 16 into 10 to the power of minus 6 divided by 10 centimeter. So 0 gets cancelled. 9 into 16, 144. Remaining this 10 goes to the numerator, 10 to the power of 10 is 10 power minus 6. Total is 10 to the power of 4. Or I can write as 14.4 into 10 to the power of 5 volts. Now these two are positive charges, therefore net potential V is given by V1 plus V2. V1 value 36 by 5. If I simplify this one, 7.2 into 10 to the power of 5. So 7.2 into 10 to the power of 5 plus 14.4 into 10 to the power of 5. So if I take 10 to the power of 5 common, so remaining 14.4 plus 7.2, 14 plus 7 is 21.4, 0.6, 21.6, 10 to the power of 5 volts. At the points where the intensity of electric field becomes 0, the net potential is. So first calculate the intensity using the known standard formula. Position of the null point, x is equal to dy root over q2 by q1 plus 1, because here the charges are like charges, positive charges. So from that we can calculate the intensity position, null point position. There we are interested potential. Potential due to positive charge is positive. So this is positive, this is positive. So net potential is the sum of individual values.